All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another exciting edition of Math 212. Let's actually jump into it. And here we go. We're going to talk about limits and continuity today. Limits and continuity in higher dimensions. Just like with functions in higher dimensions, functions of several variables as we call them, your intuition from single variable is actually going to be super useful here. Let me fix something here. Your intuition from single variable calculus is going to be super useful here. So hopefully you remember a lot about single variable limits, Lopetel's rule, what a limit is, all that good stuff. You're going to need to know all of that. And we're going to take that and we're going to put it on steroids. So just like with functions of several variables, where before we only had to keep our eye on one thing at a time, now we're going to have to keep our eyes on several things at a time. And we're going to figure out how to do this with limits. So first of all, I'm going to go, and I guess in general, we're going to do sort of the intuitive way of looking at limits. So we're not going to be going through the epsilon delta definition in details like you did in Calc 1, although I will talk about it. I will mention it at some point. But for the most part, we're going to want to have a very good intuitive understanding of limits. We're going to want to know how to compute various limits, including figuring out that limits do not exist and figuring out when they exist, how to actually calculate them. So that's what today is going to be about. And hopefully we have some time for continuity at the end. And we talk about continuity in our dimensions. We'll spend a little bit of time on that, if anything that might spill into tomorrow, but we will see. Let us continue. So intuitively, remember what a limit was about, right? So I'm talking about the single variable limit here. Limit as x approaches a of f of x equals L. What did that mean? Basically, it meant when x gets close to a, your f of x gets close to L. In other words, the limit was the y value you get close to when your x gets close to something, and this value needs to be unambiguous. And so, for example, we can look at the limit as, say, x approaches 1 of the function x plus 1. Hold on, I think I'm hearing feedback. We can look at the limit as x approaches 1 of, say, x plus 1, and you can say the limit of that is 2. And what does that mean? Well, when x gets close to 1, the expression x plus 1 gets close to 2, and it does so in an unambiguous sense. Whether I come from the left or from the right, we can look at the one-sided limits, and as we inch close to 1 from the left or we inch close to 1 from the right, we get the same y value being outputted. We get 2 as the response. And we didn't necessarily care about being at the point. Remember, limit didn't care about being at the point. It just cared about getting really, really close to the point, arbitrarily close. So we could find limits of things like x squared minus 4 all over x minus 2 and approach as x approaches 2. Now, we cannot plug in x equals 2 because we would divide by 0, but we can get close to getting close to x equals 2, and we could find the limit that way. So these were some things that you should remember about limits. Limits are about getting close. They're about figuring out what your output variable is doing when your input variable is manipulated somehow. And we had to do this in such a way that it was unambiguous. Like, I am sure from both directions, when my input variable approaches this value, my output variable will approach L, this limit. Okay. Now, intuitively, we are going to look at limits. We're going to start out with limits like this, limits of 2 variables in 3 space. So again, we're not looking at only one variable, we're looking at 2. As the coordinate x comma y approaches a certain location a, b in the xy plane, the function z equals f of xy will approach L, and we can write this down. And what that means is, as the x comma y gets close to a comma b, then your f will get close to L, right? In the same intuitive definition. And if we cannot find such a value, or there's any ambiguity in such a value, we say that the limit does not exist. So that's basically it. Now, the precise definition, there is an epsilon delta definition, and this is it here. So I'm going to talk a little bit about it, even though we won't spend a lot of time on it. So f is a function of two variables. The domain is D, and it has a comma b in the domain. Then the limit of f as xy approaches a b is L, and we write that if for every number epsilon greater than 0, there is a corresponding number delta greater than 0, such that if that expression is between 0 and delta, then our f will be close to L within epsilon. So basically what this is saying is the following. Here's kind of the picture. So this is the domain. This is the picture on the xy plane. So the xy plane is down here. So this is the picture on the floor. And basically what we're saying is that if we're measuring xy and our point is getting close to this point AB, we're saying that the y values, or not the y values, the z values or the output values will correspondingly get close to this value L. How close? Well, precisely within a circle of radius delta, okay? So AB is at the center. We imagine it's at the center of some disk. If you were to write down the equation of that disk, you'd realize it would look like x minus a squared plus y minus b squared equals delta squared, which means that you can think of your delta as being, the square root of this guy. And what you want to do is you want to be inside this circle. Or disk is a better word, but not necessarily at A. Want to be inside the circle, but not necessarily at AB. So this means you can take this expression here and you can bound it above by delta and bound it below by 0, and that gives you this guy here, right? So basically it's saying when your xy coordinate gets within that circle, meaning it's delta close to AB, it's close meaning it's within a circle of a specified radius, then the output value will get close to L. It will be within some interval of length delta around L, right? So that's what it means by limit. So I can say the limit is L if as my x comma y gets close to this point AB within that circle, then my output Z will get close to L within some interval. Okay, so that's basically what it means. As your input values get close to some region or to some point, you want to see, is your output value getting close to some point that you can know what that point is without ambiguity. Okay, now here's the thing. Remember that in single variable calculus, we had to make sure that there was no ambiguity and we had to check both sides. It turns out, however, in multiple dimensions, now we have something a little bit harder than that to be able to do. What you'll realize is that if I look at the input space here, for example, x comma y, how many ways can a coordinate approach that point AB? Well, sure, I can approach it from the left or the right. I can approach it from here. I can approach it from here. But what you can also realize is that, well, I can approach it from up here. And I can approach it from down here. And I can approach it at an angle. And I can go loop-de-loop-de-loop-de-loop and approach it there. I can approach it along this. I can approach it, go along some parabola, right? What you'll realize is that once you start bump up the dimension one more, so you're now have a two-dimensional input space, you now go from a situation where it's not just left and right anymore. It's not just the left and the right side. You have to make sure that you get the same answer approaching from all sides. There is an infinite number of ways that you can approach a point AB with a coordinate x comma y. You can approach it from all different directions along all different various paths. And essentially, for us to show that a limit exists, we have to show that no matter which one of the infinite number of paths you pick approaching that point, the f value will approach the value L. And so we don't have to check 2 points two directions here. We have to check an infinite number of directions. And we're not going to have a lot of time to do it. So that's what we're going to talk about. So hopefully you kind of appreciate what's happening here, right? In order for my coordinate to get close to A or B, my X can get close to A according to some function. My Y can get close to B according to some other function. And you put these guys together, and through various functions, various paths, I can approach A, B along any of them. I want to make sure that all of these paths give me the same answer. Okay, now that being said, it makes some things obvious about limits in the higher dimensional case. One, it's going to be a lot easier to prove that a limit does not exist than it will be to prove that one does exist in general, because you need an infinite number of paths to always give you the same answer. It turns out to get this to break, all you need to do is find two paths that don't agree. So to show that something is not, a limit does not exist, all you need to do, you don't need to check an infinite number of paths for that. You need to just find two paths that do not agree. Just like the same way in single variable calculus, if the left-hand limit and the right-hand limit did not agree, then you say the limit does not exist. In that same kind of way, if I can find two paths, left and right isn't really relevant anymore in this discussion because we can approach from all different angles. But if I can find two paths that don't agree, then we're in business. I can show that a limit does not exist. So what we're going to do is we're going to talk about showing that limits do not exist first before I show you how to prove that they do exist, because how to prove that they do exist, you'll have to effectively check an infinite number of directions. So let's start with figuring out showing that a limit does not exist. Let's do this first. Now, as always, I got your back, and there is a nice little process that you can actually check for this to happen. So here's how you would actually check whether or not that's going to happen. Steps to help in showing a limit does not exist. Well, first, what you would do is you would choose the obvious paths. What do I mean by obvious paths? Well, if you're approaching the path A, you want to approach the point A, comma B, then going along X equals A or Y equals B is kind of an obvious path to pick. So it's like you're just going along a horizontal line or a vertical line in the two-dimensional plane. And you're approaching A, B along one of those lines, either along X equals A or along Y equals B. So you're in this situation where your A, B is here. So you're either approaching along Y equals B, which means you're approaching horizontally, or you're approaching along X equals A, which means you're approaching vertically. Now, of course, you can think of two possible directions when doing that. Okay, and these are what I call the obvious paths, because those are the kind of like a brain dead idea where you just do one or the other. Just let X get close to A, see how it reacts as a function of Y. That's essentially what it's going to be. Now, by doing this with one at a time, you do the or one at a time, you can find a value for the limit, because then it will be a single variable limit. Because essentially what you can think of doing is you're setting the X or the Y equal to a constant. And basically that is equivalent to you approaching along that path. So you'll get an answer using your single variable limit idea. Now, the next step is kind of important, even though it's not an affirmative step. It's something like something that you don't want to happen. You don't want to be redundant. Remember, you want to show that a limit does not exist, meaning you don't want the same answer. You want to show that you get a different answer. So if you realize that approaching along X equals A gave you one answer, and approaching along Y equals B will give you the same answer, then don't check Y equals B. Like, you can look at it and see that you're going to get the same answer. That's not going to give you what you want. So you're going to have to approach a different path, right? So when the obvious paths won't give you different results, what you can do is choose another path. Now, the other optimal path to choose would be a path that allows you to simplify or combine expressions in the formula so that you can get to an answer a lot easier without looking at two variables at a time. So you still want to bring things back to the single variable case as much as possible. And you can do that by approaching along the obvious paths or by approaching along some path that allows you to simplify things. So that's essentially the steps, the 3 steps process. Step 1 and step 3 is what you want to do. Step 2 is what you want to avoid. So let me show you some examples. We're going to do these examples here. And as always, I'm going to take the hardest example, the first one, because got you. Okay, so I'm going to do this. I don't know, maybe I can even make this a little bigger. How about that? Yeah. All right, so here's what we want to do. So here's an example. Let's just jump in and see how we're going to apply these steps. We want to find the limit as x comma y approaches 0 comma 0 of the function xy over x squared plus y squared. Now clearly, we cannot be at this point because we would divide by 0, but the limit doesn't care about being at the point. We just care about getting close to the point. So here's what we can do. So first thing I can do is I can approach along an obvious path. So step 1. Approach along an obvious path. Obvious path has a very specific definition here, even though it sounds vague. My definition of obvious path in this case would be either go along x equals 0 or y equals 0. So here I would say along, say x equals 0. So I'm approaching along the path x equals 0. Now, if I call this L, what would this limit be? My L would be the limit as 0y approaches 0, 0. And I literally plug in x equals 0. Right? So this is like I have a function. Well, I'm in space here, and the origin is the part that I care about. And I'm approaching along x equals 0, which is the y-axis, which means I'm approaching here. I'm thinking of approaching the origin along this vertical path. Now what you'll notice, plugging in x equals 0 would give me the limit as y approaches 0 of 0 over y squared. Well, that is 0. Okay, so that's one answer. 0. If I approach along x equals 0, I would get 0 as the answer. Now, step 2, the thing you want to avoid, step 2, note that the other obvious path y equals 0 would give the same result. It's not always, you won't always know this obviously, but for this it's pretty obvious, right? We have an xy in the numerator. If I plug in y equals 0, the numerator is 0. Then if I plug in y equals 0 here, I would get 0 over x squared, and that limit would approach 0. It would look exactly the same as this. I would get the same answer. Getting the same answer is not what I want. I in fact want to show that the limit does not exist. So I definitely want a different answer. So I would skip this. So now you move on to step 3. The next best path. This is a path that allows us to combine terms. So what path would that be? Can anyone tell me a path that they think would allow us to simplify things here? Just to make sure that you guys aren't asleep. So I want to choose something, go along a path. I already did x equals 0. We're not going to do y equals 0. Tell me some other path that you think might be useful. Y equals 1. Now, y equals 1 is not a good idea. Now, let me explain why. So let's actually deal with that. That's actually very important, by the way. So I'm glad you said that. Even though it's wrong, I'm very glad you said that because I want to make sure to deal with this. Now, let's just deal with the suggestion. Yes, you should be glad. And this was a, oh my God, I'm not even going to start. If I start now, I'm going to go in on another rant, and no one needs that today. Okay, so a suggestion. Try y equals 1. Now, this is not a good path, but you need to know why, so that when you're trying your own paths, you'll know what makes a good path. It's not a good path. Why? Well, remember what we're approaching. We want to approach the origin. What does y equals 1 look like? Well, y equals 1 is a horizontal line up here. Notice this never goes through the origin. Okay, now when I say choose a path, I'm not saying completely choose at random. I am saying, remember, the point is we want to approach AB, right? That's the point. The thing that all of these paths have in common is that they're all getting close to AB. If I have a path that's going over here, like I don't want a path that's going all over there and not getting close to AB. The point of a limit is to get close to the AB, right? I want to get close to the AB and see what the output is doing, right? So when I choose a path, I'm not just choosing any random path. I want specifically a path that will go through the point that I care about. Y equals 1 is therefore not a good suggestion, okay? So just so you know, paths must go through the point. So here is another suggestion, and someone else said y equals x. Now someone says y equals x or y equals minus x. Let's go with y equals x, just because it would be simpler to apply. So here, for the second one, I would go along y equals x. Now, this is actually a nice path. One, it goes through the origin, right? So here's where I want to be. And y equals x actually approaches it along this diagonal here at 45 degrees. So it passes through the origin. It's different from y equals 0 or x equals 0. And at the same time, look at what it allows us to do. What would the limit look like in this case? Well, if y equals x, I can just call this x comma x, right? Y and x are the same. And then I literally go back to my function and I plug in y equals x. So I'm going to plug in x for x and y at the same time. So this would look like, the top would look like x squared because it was xy and my y is x. The denominator now is x squared plus x squared because my y is x. What you're going to notice this gives you is x squared over 2x squared. You would now be allowed to cancel the x squares, because when it comes to limits, we can simplify to find the limit, and we end up with the limit of a half. Now you'll realize, well, that just gives you a half, doesn't it? Right? So this is essentially becomes the limit as x approaches 0 of that, but the limit as x approaches 0 of a half is a half. Now, the thing that's special about a half is it's not 0, right? 0 is what we got before. So I approached the origin from 2 different paths and got 2 different answers. The limit does not exist. Because we approached, yeah. You've never been so happy to get something to not work out, right? Like, I'm so happy it didn't work out. It's like, yay. Because we approached from 2 different paths and got a different answer. So this means, so this is kind of like your left and right hand limits not giving you the same result in Calc 1. That's bad. No, the problem is going to tell you exactly what it is. It's literally in the statement of the problem. The limit as x comma y approaches 0 comma 0. You don't just assume you're approaching the origin. The limit tells you what it wants you to approach. Well, because why did I put x approaches 0? Because it's effectively x approaches 0, right? Because if x comma x is approaching 0 comma 0, this is the same as saying x is approaching 0, right? So essentially, by doing this, we can, in effect, change our multivariable limit into a single variable limit and just use what we know about single variable limits. Now, to generalize this, of course, if now you take a limit in four dimensions or higher, you can a lot of times do something very similar to what we're doing, but you might need to approach along a vector curve, which is a whole other class. So let's not worry about that. But yeah, so I went along x equals 0, got 0 as the answer. I went along y equals x, and I got a half as the answer. Two different answers, limit does not exist. These two paths that I tried were great paths because one, they were very simple and they went through the point that I cared about. And two, they gave me different answers. Now, just to make this a little bit more consistent here. What if we did y equals minus x? Would it be D&E as well? Well, yeah, in this case, y equals minus x would look exactly the same because you're squaring it. But down here, I would put a minus x in this position. Right, so you'd have to put a minus x down here, which is just an unnecessary complication. Like, it's not necessary. There are times when y equals x would not give you a result you would want, and y equals minus x might work, but in this case, it was not necessary. All right, so hopefully you got that. Let's do it again. All right, boom. Tell me how to show that this limit does not exist. Obvious path, which is along x equals 0. Fine, let's go along x equals 0. The limit would become the limit 0 comma y approaches 0 comma 0 of x equals 0. So the numerator is 0, 0 squared plus y to the 4th. This gives you the limit of 0 over y to the 4th, which is just 0. All right, then what? Y equals 0 would give me the same answer, right? You can see here y equals 0. If I just plug that into the numerator, I would just get 0 again. So that would be what we call redundant. We want to get different answers, not the same answers. I'm not sure what do you mean wanted us to skip. I mean, right here, it's in the statement that don't be redundant. You're only wasting time, right? If you can see two paths will give the same answer, only choose one of those paths. You want to get different results. So here, what would it look like if you did x equals y? If you did along x equals y or y equals x, your limit would look like the limit x comma x approaches 0 comma 0. This would look like x cubed on top. I would have x squared plus x to the 4th on the bottom. Right? So then that would simplify into, well, I could cancel out an x squared. And that would again approach 0. So not a great path. X squared. Y equals x squared. Okay, let's go back to the steps and maybe when the obvious paths won't give you the result, choose paths that would allow you to simplify and combine expressions. So looking at this, would y equals x squared allow you to simplify or combine anything? What would happen to the denominator? If you plug in y equals x squared, the denominator would look like x squared plus y to the plus x to the 8th. You'd pretty much end up in a similar scenario. Right? You would just have an x to the 6th in this position. And you would have, well, you'd have something else, but you'd end up with a very similar scenario. Y equals the square root of x. Okay, so now I like where you're thinking, but there was a nicer way to say that. So now you're thinking if my y is the square root of x, then that means I can take this y to the 4th and actually turn it into an x squared, which would allow me to combine with that x squared. Which does work. But you know what? Again, radicals, it would work, but wouldn't this be nicer? What about along x equals y squared? Then my limit would look like y squared comma y approaching now, if I plug in my x equals y squared, the top would become y to the 4th. The bottom would become y to the 4th plus y to the 4th. Right? So I just picked a path that's going to get the powers to be the same. So yeah, you could choose y equals x, the radical of x. You could also choose x equals y squared. The result is going to be the same. The denominator will now have two terms that's the same power of a single variable. So again, this guy here is effectively y goes to 0 of y to the 4th over 2y to the 4th. And we see that that is a half, which is not 0. This means limit does not exist. Okay, do we think we got the hang of it now? I mean, those two examples were very instructive, I think. All right, let's see if we can get through this without any hiccups. So when you get good at this and you practice a lot, you should be able to kind of just see right away the perfect two paths. All right, let's try along the obvious path. Along x equals 1 was suggested first. That will definitely go through 1 comma 0. Our limit would look like the limit of 1 comma y approaches 1 comma 0 of y over 1 plus y minus 1. So that is effectively, now we only care about what the y is doing, and it's just y over y. So that's 1. Okay, what else? X equals 0 is not a valid path. X equals 0 is the y-axis, and that does not pass through the point 0, 1 comma. Y equals 0 won't work. Why will it not work? I agree with you that y equals 0 will give you 0. And that's not what you want? Think about what you just said. Right, that is totally fine. The other obvious path works here. If I go along y equals 0, which is another obvious path, I'm not going to skip it this time because it actually gives me a different result. The limit is going to look like 0 over, it's going to be the limit of 0 over x minus 1, which gives me 0, which is not equal to 1, which I got before, dne. So the fact that it does not work means it works to show that the limit does not exist. Maybe that's what it meant. But it's anyone's guess at this point. Yes, you want to get different paths. So that's to say, you want different results. We're in a situation now where we actually want to not get the same answer. We want to show that a limit does not exist. That's the thing that I'm teaching you right now. And there are some times when a problem is stated specifically in that way. Show that the following limit does not exist. And your goal is to find two different paths. There are times when you're just told the limit, but you're not told whether or not it exists, and you have to do kind of figure it out on your own. We'll deal with that scenario when we get to it. So here, both obvious paths actually worked. I didn't need anything too exotic here. All right, here's another example. All right, go. Along x equals 0. Fine, let's do it. Along x equals 0, our limit would look like 0 comma y approaches 0, 0 of sine squared y over y squared. So this is effectively the limit as y approaches 0, well, of sine squared y over y squared. What is that? It's 1, correct? That's a special trig limit, right? Sine y over y as y approaches 0 goes to 1. All right, what else can you think of? Y equals 0? Let's see. Along y equals 0, our limit would look like the limit y equals 0, my sine of 0 would then be 0, and my y squared would be 0, so I would have x squared over 2x. Oh. X squared over 2x squared. That's equal to a half, which is not 1, which is what we got before. Limit does not exist. Awesome. Yay, it didn't work out. Yay. We should celebrate that it didn't work out. Which again is kind of going into my rant. This is a nice topic because it makes you excited about failure, which is what I was going to rant about earlier when we had that wrong. Where's I think I lost one of the guys. Let's do this. Oh, there he is. Okay, I had to grab those two. So hopefully you're getting the hang of it. I assume by those few examples you would have gotten that. Well, the obvious paths is a great start because it's usually easy to figure out the answer along one of those paths. You only get more complicated if you have to. So the obvious paths are computationally easy to think about. All right, this one. So hopefully you're getting the hang of it. Try this limit now on your own. Maybe I'll give you 2 minutes and you guys can tell me 2 different paths and let me know what's up. So this is the problem right here. Everyone do it on your own, write it down. I'll give you guys 30 more seconds. Okay, all right, let's see where you guys up. All right, so I just went and got some more coffee. Have you ever been in a situation where it's like, on one hand, you need some coffee to get going, but on the other hand, you have to be up early tomorrow and you're not sure if you're actually messing up the little sleep that you're going to get. First world problems. There's not enough dip for my chips, but if I open another dip, then there won't be enough dip or too much dip from the chips. Okay, let's go. All right, so obvious path, someone's like x equals 0. All right, let's do it. Sounds like a great idea. Along x equals 0. So our limit here would look like the limit, well, 0 over y squared. Awesome. So that would give us 0. All right. So y equals 0 would obviously give us the same thing, right? I mean, y equals x. Okay, yeah, y equals x. Why not? Worked last time. It allows us to combine the denominators. So L equals the limit xx approaches 0, 0. And if my y equals x, I would get x cubed over x squared plus y, x squared plus x squared. That will give me the limit as x approaches 0 of x cubed over 2x squared. And well, this would cancel into that, and I would get x over 2. That's again going to give me 0. Okay, any other ideas? X squared equals y. Okay, so along y equals x squared, the limit would be if I do y equals x squared, that would give me x to the 4th in the top and x squared plus x to the 4th in the bottom. Then I'd be able to say factor out an x squared and cancel. And that gives me 0 again. Still getting 0. You know what works sometimes? Sometimes you can go along like y equals a constant times x, where x is a constant, to see what would happen. And you can have L is equal to the limit as, well, you know, as x comma kx approaches 0, 0. All right, so if y equals kx, so that would look like kx squared, kx cubed over x squared plus k squared x squared. Right, now sometimes the limit gives you some function of k, in which case you can say, well, for different k values, you might get a different value. Okay, so what is this going to look like? Well, again, we can cancel the x squares. So that'll give me kx over 1 plus k squared, and that's equal to 0. So didn't work. Y equals y to the half equals x, meaning x equals radical y. Abdul Rahman, what do you mean? Am I messing with you? What do you take me for? You know, just because you guys can't come up with a path doesn't mean. You know, see this, y equals 2 won't work. Y equals 2 does not go through the origin. Okay, the jig is up. It does exist. I was messing with you guys. It does exist. I knew it. All right. So this, we've actually encountered someone who does exist. Now, to be perfectly clear on this, we didn't show that it does exist. But at this point, we didn't prove this, but my gosh, it's getting suspicious at this point. Suspicious. So here's the beauty of this method. And this method isn't, I wouldn't really say it's a method that works very well in the general world of math, but for a Calc 2 class, for sure, this method is awesome. So this method isn't, like I said, it's not general, but in a Calc 2 class, if this method can't show you that a limit does not exist, then probably the limit exists, which now we're going to get into the question of dealing with that. There are going to be times where you're going to have a limit and you're not going to be sure whether or not it exists. Now, the reason why you don't want to be redundant is because in such a scenario, the best approach would be first try to show that it does not exist because it's going to be easier to show that in general, but you don't want to waste a lot of time showing that something does not exist. So you want to be very efficient with the paths that you choose. By following this three-step method here, you can choose very efficient paths, and it should give you a very good idea of whether or not the limit does not exist within 2 tries. So at this point, when you follow that strategy I gave you, and this path, the obvious path here, and the not so obvious path here, both gave you the same answer, after 2 steps, it's already suspicious, right? Like after here, you should be thinking suspicious. So I don't want you to go into like an exam or something, trying to prove something does not exist, and you're trying like 5, 6, 7, 8 paths. Like, no, you're wasting a lot of time. You need to be able to quickly determine within like 2 tries that the limit does not exist. And then your tries are going to be so great such that if they don't work out to show that it does not exist, then chances are it does exist. And then you work on showing that it does exist. Now, showing that it does exist, as I said, showing a limit exists, it is very different. You need to effectively check an infinite number of paths. All of them. Now, of course, there's a mathematical trick we can use to do this, but theoretically, that's effectively what you want to be able to do. Right. So yeah, that was Abdul Rahman spotted it first. He was like, yo, I think this dude's messing with us, man. And this cat, look at him. He's around here playing with us. But on the other hand, this is going to be memorable, I think, which is the point. I want you guys to remember this feeling. I don't want you guys to be in a test wandering aimlessly and not even know that you're on the wrong path, pun intended. So I want you to be able to know when something feels off, when you might have to change your tactics. Following my strategy, which at this point, going through these few examples, I think you guys are getting a pretty good handle on it. If that strategy doesn't give you the results that you're trying to get within like 2 tries, you should automatically be thinking, maybe it exists, right? There are times when you're not going to know for sure, and you need to know when to stop the process before it gets out of hand. So this was about getting out of hand. So now I'm actually going to show you how to show that a limit does exist. Here are some things to keep in mind when assessing limits, though. let's move these guys up here. Now, showing that a limit exists, we're going to use the squeeze theorem, believe it or not, our old friend, the squeeze theorem. So now this segues into the next part of the lesson. How would you show that a limit does exist? So as I mentioned here in the first bullet point, if you're not sure whether the limit exists or not, check that it doesn't exist first, right? And again, you must choose paths that pass through AB, right? So I knew someone might suggest a path that didn't go through the point. So for example, if A comma B is 0 comma 0, then along x equals 1 is not a valid path to choose. So in the event that you're not sure whether or not a limit exists, sometimes you'll actually be told directly, point blank, it doesn't exist, show it doesn't exist, but not every time. In the event that you're not sure, check that it doesn't exist first. Do it using the process that I gave you. This will cause you to be very efficient, and within 2 tries, you'll know pretty well whether or not it exists. Not a guarantee, but in all likelihood, if doing that strategy didn't work out, then it doesn't exist. Make sure you choose the right paths that go through the right answer. So if you chose a bad path and got different answers, you can prove that a limit does not exist when it actually exists, but that's because you messed up the problem. You actually didn't go through a path. Following the 2-step strategy gives you an efficient way to stay efficient. If suspicious the limit exists, you must prove it. And for that, you can see below. Let's talk about finding limits. Showing a limit exists is more challenging than showing it does not exist. But we're not going to use the epsilon delta definition because in the higher dimensions, that's really annoying. We're going to use something called the squeeze theorem. And it's your same old friend, the squeeze theorem from single variable calculus, but we're going to apply it in another theorem to show that when a limit exists. And here is the first way to show that a limit exists. It's also a theorem in your book, but I forgot what the number is. Suppose you have f of x, y is defined at points arbitrarily close to a comma b, right? You have to be able to approach a comma b arbitrarily close. If there exists some other function g such that your f of x, y minus L is less than or equal to g, and at the same time, g approaches 0, specifically 0, always 0, then it means that the limit of f of x, y is L. Now, why is this difficult, quote unquote, is that g is not going to be handed to you. You need to find this guy. You need to find a g, right? Such that this is work, and the limit of g as you approach the same AB, always 0, specifically 0. And then, if you can do these 2 things, find a function such that f minus L in absolute value is always less than or equal to that function, and at the same time, and by g, I didn't really mean Kayla necessarily, such that f of x, y minus L is less than or equal to g, and at the same time, the limit of the function g that you found approaches 0, then that is a way of showing that the limit approaches L. Now, L is your proposed limit. So the L here is the proposed limit, what you think the limit is. Now, in our example above, what would you think that the limit is? If the limit exists, what do you think it would be? Zero, right? Because all the paths are approaching 0. So if the limit does exist, it would have to be 0. So in this scenario, I would plug in L equals 0, and then I would try to find a function that's bigger than or equal to f in absolute value. Now, why does this work? Suppose we can find such a g. Then this means in absolute values, f minus L would be less than or equal to g. what this means is that you can break the absolute values down much as you could before. And f is like a multivariable function here, but it doesn't matter. I can add L to both sides. And then I can take the limit of all sides. Limit of this, limit of this, limit of this. Now, this would give me the limit of L minus the limit of G is less than or equal to the limit of F, less than or equal to the limit of G, plus the limit of L. Now, what did we know about the limit of G? The limit of G approaches 0 by assumption. And what does the limit of L approach? This approaches L because L is a constant. This also approaches L because L is a constant. And so what you end up saying is that L is less than or equal to the limit of F, which is less than or equal to L. In other words, your limit of F must be equal to L by the squeeze theorem. Right? So this is the goal. As long as you can find such a function G, you're golden. Find a function such that this absolute value inequality holds, and at the same time, the limit of this function goes to 0, and it's guaranteed that the limit of f will approach L. And of course, you're taking the limit that you're given, limit of as xy approaches AB, whatever you're concerned about. Okay, so let's apply it to this guy. The guy that almost made a fool of us, but Abdul Rahman was watching out. Now, here's what I want you to realize that we want to do. We want to find g of xy such that f of xy minus 0, which is what we think the limit is less than or equal to g of xy, and the limit as xy approaches 0, 0 of g of xy, and it's 0, 0 because this was the given limit. It's not always 0 here. I want that to equal to 0. Then that would mean that the limit as xy approaches 0, 0 of f of xy would be equal to 0, the 0 that's here. So there's a 0 for the g, and this is always a 0 here. This guy, though, not always 0. It's whatever you think the limit is. So I don't want you to mix up those two zeros. That's why I put this 0 in a different color. Not always 0. It is whatever you think the limit is. Okay, so let's do that with this guy. So we see here, so we're suspicious the limit is 0. So you went through the process of trying to show that the limit does not exist. And then, well, I'm going to apply it to the problem now. For what? So we're suspicious the limit is 0. Why? Because I tried that badass method that we had from before and it kept giving me 0. Very suspicious. I'm thinking the limit is 0 at this point. So what I'm going to do, I think the limit is 0. So now what I'm going to do is I'm going to set f of x x squared y over x squared plus y squared minus the 0. And I want to find a bigger function whose limit also goes to 0. Now, again, your intuition from Calc 1 limits is going to be very important here. Your intuition from comparison theorem for series is going to be important here. We're applying the same idea with the comparison theorem for improper integrals, for series, and for squeeze theorem from Calc 1. We can figure out our function g. It might seem daunting. How do I find this function g? There's an infinite number of functions out there. But your g is going to ultimately be very close to whatever this expression is, because you're going to find the g by just manipulating that expression. So what I can do is start to manipulate this expression. And I want to manipulate it in such a way that I would get something larger. Now, can you tell me some way to manipulate this expression to get something larger? How can I get something bigger? Anyone? Right? You can make the denominator smaller. That's one way to get something bigger. Can you tell me a convenient way to make the denominator smaller? Give me a convenient way to make the denominator smaller. X squared plus y squared will never equal 1, right? Because x and y is approaching 0, comma 0. Smaller denominator equals. Like I said, it's the same thing that you would have done for squeeze theorem or comparison theorem. Right, you can remove the y squared from the denominator. Your y squared is going to be 0 or larger, and so if you remove it, you will make the denominator smaller. So that's going to be less than or equal to. Now what's nice about this is that the x is actually simplifying, you just get y. And what do you know about that? This approaches 0 as xy approaches 0. So hey, you guys just found g, look at that. Of all the infinite functions out there, you guys found your soulmate that will get this to actually work out. So all I have to do is take g of xy equals the absolute value of y, and we've proven the limit as xy approaches 0, 0 of x squared y. Yeah, we found Kale in the haystack. Equals 0. We found the g. The function y, absolute value of y, will work. Because f of xy minus L is less than or equal to this function, and that function approaches 0 as I take the limit. So we've just proven that the limit equals 0. Using the squeeze theorem. And effectively, this checks from any direction, infinite directions, because we're literally applying a theorem that we know is true for absolute values in all directions. Now, there are other methods to show that a limit exists, and I will get to them presently, but for now, let's get the squeeze theorem down. These are limits that exist. And I want you to show it. So here's another one. All right, someone show me that this exists. So first, best practices. If unsure, try to show does not exist first. Okay, so let's check if it does not exist. All right, Abdul Rahman, on top of it. How would you check? Tell me how you would check if this does not exist. Right, x equals 0 is an obvious path, so go along x equals 0. It's clear here the limit would be 0 because you get 0 over like y squared. Another path that you won't obviously get 0, so you don't want to force it. So here along y equals x. This will allow us to combine the denominator. So this is going to be the limit of 2x squared sine of x over 3x squared. These two guys would cancel. You'd have 2/3 sine x, and hey, that approaches 0 again. So at this point, with those two paths, suspicious. Right? So if this were like a quote unquote real world scenario, you're in a test and you do this check, at this point you're suspicious. It shouldn't take you 10 tries to get suspicious that this guy exists. So now you're suspicious. Maybe the limit is 0. Now you don't know, you cannot know from checking only two paths. So now you go into this process. How would you actually show that this is 0 by the squeeze theorem? So I want to prove this is 0. What do I need to set up? Inequality with less than or equal to 0, and try to make the denominator smaller, or you can make the fraction bigger. So what you can do is do the guy here. It was, what is it? 2x squared sine y, 2x squared sine y over 2x squared plus y squared minus the proposed limit of 0. Now that's of course equal to 2x squared sine y. How can I do that? Right, again, remove the y squared. That's smaller, these guys would cancel. And so this gives you now sine of y. And nice thing about sine of y is it approaches 0 as xy approaches 0, 0. So take g of xy, that's g. That's g equals this. And that means that the limit of 2x squared sine y over 2x squared plus y squared equals 0 by squeeze theorem. Now, I do want you to notice something. Just like before, where it was possible to choose a bad path, warning, it is possible to make the wrong choice here as well. So be careful. Don't just willy-nilly, oh, I'm just going to always subtract the y squared. It always seems to work out. No, be careful. So let's go back to this example, I think is going to be a nice illustration. So for example, if you go back to this guy, notice that if here we try to set up What if we had taken away the x squared instead? So in this case, remove the x squared. Now, it does cause you to get a larger fraction, but it's the wrong move. Why would it have been wrong to get rid of the x squared as opposed to the y squared? Well, this guy, you should notice, would now look like x squared over y. And now you end up with a division by 0 scenario that you'd have to deal with. Right, so you can't remove the denominator. Right, so at this point, this limit would not exist. Now, it's not the original limit, so the fact that this does not exist doesn't actually break the problem. However, it just means that this function cannot work as a g, right? So this is not a g. This guy's just posing. He does not satisfy the requirements. So it's possible that you can do things that make sense in general, in the sense that you'll get something larger, but at the same time, you have to make sure that that thing is going to make sense with the limit that you started with, and it will give you the result that you want. Namely, you always want the g to go to 0. So that limit's not going to go to a 0. We cannot use it as a g. Haters. That's how I know Kayla's a G. She's literally like eating her dinner while I'm over here working. Okay, let's, what about this one? Check if it the NE. Right, so, I mean, there's something else that's jumping out here, but let's see if someone sees it. Check DNE, if you go along x equals 0, you would get L equals minus y to the 4th over y squared, and you're taking the limit of that. That is just the limit of minus y squared, which of course approaches 0. And if you go along y equals x, then you would get the limit of 0 over 2x squared, which is also 0. So at this point, you're suspicious. Yes, it can be simplified. So our good old friend, difference of squares. Now, remember, just like limits in single variable calculus, your intuition still works in that regard. If you can simplify so that you can plug in a number, you are allowed to do it. This guy actually simplifies in the sense that we can actually apply difference of squares here. That guy would cancel. And then I can literally just find the limit as xy approaches 0, 0 of x squared minus y squared. This would be 0. So this limit exists, and you can do it by direct computation, right? Now, you won't always be able to do that. Like in this example, you can't really do that with a direct computation. In the previous example, you couldn't really do it with direct computation, but you can do it with direct computation in a lot of cases, in some cases. And again, squeeze theorem would still work here. So if you went, squeeze theorem still works, but would be longer. So for example, I can, and you'd end up having to do a similar thing, you'll notice. Like if I had this, you'd realize removing either the x squared or the y squared is a bad move, right? So hopefully you notice that. The better move is to actually do the same simplification. So you end up doing it anyway, and it doesn't really save you space. So I would actually, again, jump into difference of squares here. These guys would actually cancel. And then I would get this guy, x squared minus y squared, and that approaches 0 as xy approaches 0, 0. So take g equals this, and that means the limit of f equals 0. So, as is often the case, several ways to skin a cat, but this is by far the preferred method. If your old algebra skills are useful, there always should be at the tip of your tongue. Algebra is always going to be useful, no matter how high you go in math. Even this reminds me of a meme. So this meme. I think goes like. How does it go? Let me see. Higher level math with the ability to do simple math. And it's a decreasing graph. or was it the other way? I think it's the other way. I think it's the other way. This guy goes down here. Ah. You don't believe me? Go find a random Calc 3 student and test them on pre-calc. Chances are they really suck at it. Heck, I'm one to talk. I suck at arithmetic. I guess sometimes it's like, it's just sometimes simple math just gets you bored after a while. Like right now, if I do arithmetic, my brain just literally, I want to do anything else. But don't let this be you. Turns out, kids, as far as an undergraduate degree is concerned, there are really complicated problems out there, but for an undergrad, there is no real complicated problem. Your complicated problems are just a combination of little smaller problems. And it turns out the better you understand the simple, it's the better you'll understand the complicated. That'll be true up to like a master's degree. Let's, do you have another example? Oh, that should be the YouTube thumbnail. There you go. I mean, there are tons of memes like that. XKCD, you guys should know about that. All right, here's another method. Polar coordinates. You remember our old friend polar coordinates? it provides another computational way. Did I miss any examples? I don't think so. I think I got all of them. Polar coordinates, our old friend, which we saw forever ago, which in the summer semester is like 2 weeks ago. This allows us, well, let me move this up. This gives another computational approach to finding limits. This is going to be really cool. At least I think it's cool. So recall, in polar coordinates, what is your x? What is your y? X equals r cosine theta. Y equals r sine theta. What about, is there an equation that you can get the r from the x and the y? Equation that relates r, x, and y. What is that? Polar coordinates. Right, we also know that x squared plus y squared equals r squared. Now, here's the cool thing about that. As xy approaches 0, 0, what does r approach? It would approach 0. So look at what's going on here. I'm in a situation where I have two variables approaching 0. However, I can re-envision that situation as a single variable approaching 0. Hopefully you see where I'm going with this. So, especially in the case where you see expressions like x squared plus y squared, that is very, it turns out to be very useful. So let's go back to this guy, the same guy that made a fool out of us. We're gonna do him in another way. So we're gonna end this man's whole career, right? Literally show him he ain't nothing. We can solve you in multiple different ways, all right? So here's another way to solve this guy. Switch the polar. Gonna end this man's whole career. Okay. Switch the polar, what's gonna happen? I can now, instead of x comma y approaching 0, 0, I can literally look at this as r approaching 0. I'm now back in single variable limits territory. What does this mean? Wherever I see x squared plus y squared, I can replace with r squared. Wherever I see x, I can replace with r cosine theta. Wherever I see y, I can replace with r sine theta. Now, look at what happens. Well, this x squared is going to cancel that x squared. And so I would have r times cosine squared theta sine theta. And what's going on with the r? Well, the r is approaching 0. And so what happens to this limit? It has to approach 0, no choice. Boom, another way. Now, you could also show, just to make sure that you're paying attention, if the result were a function of theta, we could conclude the limit dne since the value changes based on theta. I Was I know I heard this song on the radio the other day when I was driving, heading on a road trip or something, and I forgot what it was. Anyway, there was a song, I think it's very popular, and it was like someone was using "were" incorrectly in the song, and I was like, did anyone actually point that out? I don't know, it just came to me when I said that. Okay, so polar coordinates, look at that. Boom. Look at this guy. So you see this guy here. Another example. Look at that. Looks terrifying. So you look at this, and then, no, it was like a pop. It was a pop song. If I was a man or something like that, I don't know. Anyway, so you look at this, x squared plus y squared times ln of x squared plus y squared, as y is approaching 0. Now, at first, that looks very complicated. Then, what would we get if we actually switch the polar, though? Now, notice here, if we switch the polar, we can think of this as r approaching 0 of r squared times ln of r squared. All right, now, how do I find that limit? What do you mean derive? Lopetel's rule. Why would you need Lopetel's rule? And can you apply Lopetel's rule here? It is an indeterminate form. You'll notice that this would approach 0 times infinity. In fact, 0 times negative infinity. So it's an indeterminate form. How do we deal with indeterminate forms? So you're thinking of Lopetel's rule. But it doesn't apply to 0 times infinity. So what would we do? Integral that won't apply here. We don't need squeeze theorem. Abdul Rahman, you're getting colder. You were warmer before. Lopetel's rule is what you would do, but you cannot apply Lopetel's rule to 0 times infinity. Lopetel's rule applied to what indeterminate forms? No, not 0 over infinity. In fact, 0 over infinity is not indeterminate. It's at 0. Infinity over infinity is one of them, plus or minus, or 0 over 0. You need to get one of those two to apply Lopetel's rule. How can I get one of those two here? So it's going back to Calc 1 all the way in the spring. Lopetel's rule involves you taking the derivative of a numerator and a denominator, but you cannot do it here. Right, you would move someone to the denominator because Lopetel's rule does not apply otherwise. So I would move this guy down, right, as r to the minus 2. Now, this guy approaches, well, if my r gets close to 0, that would approach infinity. In the top, well, negative infinity. And in the bottom, as my r approaches 0, it would also approach infinity. So Lopetel's rule applies now. So here, I can apply Lopetel's rule. Lopetel's rule says to find this limit, if the limit exists, then it will be the same as taking the derivative of the top divided by the derivative of the bottom. The derivative of top is going to be 2 over r divided by the derivative of bottom minus 2r to the minus 3. This is going to be the limit of minus, I want to say r squared, which now as your r is approaching 0, that's 0. So you'd have to remember your old Calc 1 rules, squeeze theorem, Lopetel's rule, all that good stuff. So some of you might think that the polar coordinates way is easier, but then you of course have to have the skills to pull it off. Like if you switch the polar coordinates and then you end up with an indeterminate form, you need to know how to deal with it, right? So it is going to be assumed that all your Calc 1 techniques you're on top of all your Calc 1 techniques. So that was another example. It makes your like limits from Calc 1 seem silly by comparison now, doesn't it? Again, just to make sure, I want to cover my bases. Usually these things go without saying, but there's always someone who doesn't recognize it. So there are some obvious mentions that I need to do. Obviously, step 0 of your limit process, if you go back to Calc 1, is you always try to plug in the number first. So that is still also very doable. So if I see this, the first thing that essentially I want to do, step 0, is just try to plug in. I could literally just plug in 0 for x and 0 for y and get minus a quarter, right? So if you see a limit like this, I don't expect you to do a squeeze theorem. I don't expect you to use polar coordinates. I don't expect you to do anything but plug in the number. So you really do the things that I mentioned before, switch into polar coordinates, using squeeze theorem, using all these sophisticated methods. Really, you do those after you've exhausted all your Calc 1 methods. So just to see if you're paying attention, I might throw a problem at you where a Calc 1 method can deal with it, and where if you try to do something that I taught you, you would get the answer, but it would really be a waste of time. So you really should remember all your Calc 1 stuff. Similarly here, here's something that another a Calc 1 technique can also handle. So simplifying and plugging in works. You see something like this. You cannot plug in x equals 1 because you divide by 0, but you can factor out a y. You can simplify this. How would you simplify this to be able to plug in x equals 1? Ideas? Sure, you could multiply and divide it by the conjugate of the denominator. There's an easier way though. At least I think it's easier. Something that's a little bit more elementary than that. That could work though. The top is the difference of squares. Which is a lower level technique than multiplying divided by conjugate actually. So now you just have the limit of y times radical x plus 1, and you're plugging in x goes to 1 and your y goes to 2, so the limit here is 4. Now, again, you could potentially do like the squeeze theorem. You could also do things like switching to polar coordinates, but they would be very much overkill for a problem like this, where it's just like difference of squares or plugging stuff in. Now, I really wanted to get to this today. This is going to spill into tomorrow, but I mean, it's okay. So we're going to talk about continuity in higher dimensions. Of course, if you recall continuity from Calc 1, you would know continuity does involve looking at limits. So that would be the next step. And we will do that tomorrow. Well, hopefully it was kind of fun. All right. Next week, Thursday, we don't have classes at all. We're going to definitely be finished by this Thursday. Sure. I'm open to having a review for the final. We can meet on Monday, even though technically we don't have a class registered. If enough of you want to meet, I'm willing to meet next week and do some review. Oh, the date of the final has been set since the very beginning. It's even in the syllabus. The final's on the 23rd, which is next week, Thursday. In terms of how you should be studying for the final, I posted a final exam review on the website. So you'd probably start there. Yes, it's still multiple choice on Blackboard. In the spring semester, it was 25 problems that you had 2 hours and 15 minutes to do. Which, I mean, in the grand scheme of things, you guys would definitely be able to do more than that in the time if you've been practicing from my tests, right? Yes. So Saturday, 12 to 3. But yeah, for our test, I literally had you guys do 20 problems in an hour and a half. So giving you 2 hours and 15 minutes to do 25 problems should be a cakewalk. I mean, the in the grand scheme of things, that's what I want. I want you guys to be like, the final exam is a step down. It's not anything to be anxious about. It's like, seriously, they made me wake up for this. All right, let me just end this man's whole career and go about my business. That's what I want the final to feel like for you guys. Anyway, we'll stop there. We'll talk about continuity tomorrow. We won't spend a lot of time, but I wanted to also show you some graphs, which I think are going to be is going to be pretty cool. For now, we will stop there. So hopefully that was enjoyable. Hopefully you also understood it. Remember your limits. A lot of the intuition from Calc 1 is still very useful. And whenever a Calc 1 technique would work, it should work. However, squeeze theorem or switching to polar coordinates is a good way. It's a higher level way of showing that a limit exists. You should also know how to show that a limit does not exist. And a lot of times you might be told that a limit does not exist and you have to show that it does not exist. Sometimes though it will be ambiguous. They'll say, determine whether or not the limit exists and find it if it exists, or show that it does not exist. And you're like, I don't know. Well, you just do what I told you, apply your Calc 1 methods. Those are like your step 0. Then check that it does not exist using 2 paths. If you do more, your chances are you're wasting your time. And then if you get the same answer, you can just go in with, yeah, I know. I noticed that Jason wasn't here. I don't know what's going on with him. Anyway, I will see you guys in the next one. Enjoy your night. Everyone stay safe. And I will see you guys in the next one. Ciao.